Today, we are going to finish our discussion about disaster recovery for containerized applications on OpenShift. Hey, what's up everybody? Welcome back to my channel. My name is Aleš Nosek and I'm the software practitioner located in San Diego, California, helping you navigate the world of Kubernetes. This is the second video in the two-part series. If you missed the first video, see the link below. Last time we discussed this architecture, which spans two AWS regions, primary and secondary. This architecture allows us to recover from a disaster in the primary region by failing over to the secondary region. In this video, we are going to talk about how we implemented traffic routing so that we are able to fail over the traffic from one region to the other. We will also discuss the data replication between the two regions in more detail. And in the last part of the video, we will talk about how to deal with applications that got into an undefined state due to a disaster. So let's start with the first topic, which is traffic routing. In the active-passive disaster recovery scenario, the application traffic is all routed into a single region, into the active region. The other region, which is passive, doesn't receive any application traffic. In the case of a disaster in the active region, the application traffic must be rerouted to the region which has been passive so far, and with that, the role of the passive region changes to active. The question now is, what mechanism could we use to reroute the traffic? In our case, the application clients that need to be able to connect to our applications running on OpenShift clusters. These clients can be deployed anywhere, if it is on-prem or in the cloud. And also, in our case, we do not control the configuration of these application clients. That means we cannot, for example, reconfigure them to connect to the other region. There are two common approaches that can be used to reroute the traffic between regions. There is anycast routing and there is DNS-based routing. With anycast routing, your application is assigned an anycast IP address, and this IP address can be announced either in the primary or the secondary region, depending on which region you want to have as active region. Application clients will open a connection to the anycast IP as their destination IP, and the traffic sent will be automatically routed to the active region. On AWS, you can use the AWS Global Accelerator service. This service provides public anycast IP addresses. Unfortunately, in our case, our applications are not facing the public internet, and so we needed private anycast IP addresses. After some research, it was not clear to us how we could implement the private anycast IP addresses on AWS. If you have an idea how we could get this done, please share your idea down below the video. I will be very interested, and others as well, how this can be done. So for traffic routing, we ended up using the DNS-based routing, which worked very well for us. In DNS-based routing, each application is assigned a record in DNS. This record is a CNAME record, which points to either the primary or the secondary region. To failover the application traffic between regions, we just need to go and update the record in DNS. This diagram depicts the DNS-based routing in more detail. At the top of the diagram, you can see the Route 53 private hosted zone. That's where we create the DNS records for our applications. At the bottom of the diagram, you can see two OpenShift clusters. There is the primary OpenShift cluster and a secondary OpenShift cluster. The application client in the middle of the diagram is trying to connect to the application running on our OpenShift clusters. The client first resolves the hostname of the application by querying the Route 53 DNS. Based on the CNAME record, the DNS will either return the IP address of the ingress router of the primary cluster, or it will return an IP address of the ingress router of the secondary cluster. The client will use the returned IP address to connect to the currently active region. We use the external DNS operator to manage the DNS records in Route 53. DNS record is a global resource which can be managed only from one place to avoid any conflicts. And so we deploy the external DNS operator into the secondary region only. This allows us to trigger the application traffic failover in case that there is a disaster in the primary region. The external DNS operator watches a custom resource called DNS endpoint, and using this resource, we can exactly define how our DNS record should look like. In this example, we created a wildcard DNS record, which will match all applications on one cluster. The traffic to these applications will be routed to the cluster in the west region, which is our primary region. The DNS endpoint resource is managed using GitOps. If we want to fail over the application traffic from primary to the secondary region, then we need to update this one line of the target cluster to the secondary cluster in Git. After we push the change to Git repo, Argo CD will pick it up and sync it with the secondary cluster. From there, the external DNS operator will notice the change and will update and propagate the change to the Route 53. After several minutes, when the DNS cache expires, the hostname of our application will resolve to the IP address in the secondary region, and the application client will then start sending the traffic to the secondary region. In the previous diagram, I showed you an example of a wildcard DNS record, which is used to reroute the application traffic for all applications on the given cluster. In addition to the wildcard record, we are also able to create individual DNS records, and those records match only a single application. In DNS, if there are two records which both match the application hostname, the wildcard record and the application individual record, then the individual record is a better match and it will take precedence over the wildcard record. This allows us to use the individual DNS record to override the application routing for a single application. In regards to the traffic routing, there is one last point I want to explain. When the application request hits the ingress router, the destination for this request will be set to what we call the global application hostname, and this global hostname is normally not known to the router. To allow the router to correctly forward the request that uses a global hostname, we have to create an additional route. So each application will be deployed along with two routes. The first route is a cluster-specific route. This route allows to forward requests which include the domain of the cluster in the destination hostname. And the second route is a global route. This route allows to forward the requests which use the global hostname as their destination. And with that, follow me to the next part of the presentation, which focuses on data replication. Data replication methods can be divided into two groups. These are backups and continuous replication. Continuous replication can be further divided into synchronous replication and the asynchronous replication. As I mentioned in the previous video, we use backups to protect against the deletion or corruption of application data. And we also use backups for the backup and restore disaster recovery approach for recovering Red Hat ACM. The backup process typically consists of two steps. First, a snapshot of the data is created, and then the snapshot is copied out of the original storage. Both steps are required to create a proper backup. If you would only create a data snapshot, then in the case of the failure of the storage, this snapshot will be gone as well. The important part is that the snapshot must be copied out of the original storage so that you can use it later if the storage fails. We can use it later to restore the data. An important keyword in regards to the backups is the crash consistency. Some storage solutions are able to create a crash consistent snapshot or backup. This means that you can create the backup even when the storage is being written to at the same time, and the resulting backup won't be corrupt. On the storage side, this can be achieved using a copy on write technique. If your storage doesn't support crash consistent snapshots or backups, then you will need to make sure that nothing is writing into the storage while you are creating the backup. You can achieve that by, for example, shutting down your application before creating the backup, or by freezing write IO operations using fsfreeze. Let's now focus on the continuous replication. Using the two slides, I would like to explain the difference between the synchronous and asynchronous replication. Let's review the synchronous replication first. The diagram depicts the sequence of actions that take place when a client is trying to write a block of data. The client sends the block of data to the storage in the primary region. This storage will write the data to the underlying media, and at the same time, it will try to replicate the block of data to the storage in the secondary region. Both these write operations are executing synchronously. It means at the same time. The result of the whole operation depends on the results of both write operations. If, for example, the write to the secondary replica fails, then the whole operation failed. In this case, the client will need to retry the write operation. With the synchronous replication, the write operation succeeds if, and only if, the block is successfully written to both the primary and the secondary region. The benefit of the synchronous replication is that no data is lost even when there is a disaster in one of the regions. That means that with synchronous replication, you can achieve a recovery point objective that is equal to 0. When comparing synchronous and asynchronous replication, there are two downsides of the synchronous replication. Number one, the write operation takes longer because the operation can only complete if writes into both regions are complete. Number two, from the standpoint of the client, the write operation is less reliable because the operation succeeds only when writes into both regions succeed. These two shortcomings are especially a problem in scenarios where the network connection between the primary and the secondary region is too slow or not reliable. In this case, the synchronous replication may perform very poorly, even to the point where it is practically not usable. Let's now take a look at the asynchronous replication. This diagram depicts the sequence of actions that take place during the asynchronous replication. The client sends a block of data to the storage in the primary region. This storage will write the block of data to the underlying media, and at the same time, it will try to replicate the data to the storage in the secondary region. As soon as the data is persisted in the primary region, the whole write operation returns success to the client. At this point, the write operation to the secondary region may have not completed yet. As we can see in the diagram, it actually took 2 attempts before the data was successfully written to the secondary region. If the storage in the primary region would fail before the data was successfully replicated to the secondary region, then the data is lost. That's why the recovery point objective of asynchronous replication is greater than 0. In other words, the asynchronous replication cannot guarantee that there won't be any data lost during a disaster. So why would you ever prefer using asynchronous replication to using the synchronous one? If the connection between the primary and the secondary region is too slow or not reliable, the synchronous replication may not be able to perform well enough, and in this case, you are pretty much left with using the asynchronous replication. Replication tools can be divided into 2 categories. We have replication tools which work on the application layer, and then we have storage solutions which replicate on the storage layer. Application layer tools understand the data they are replicating. These tools have been specifically designed to replicate that kind of data. The examples of application-specific tools are the Oracle Data Guard asynchronous replication, the Postgres SQL replication, MySQL dump, but also the Kafka Mirror Maker 2, which we used in our architecture. The advantage of these tools is that they provide application-specific features. For example, you can choose only some of the database tables that should be replicated, as opposed to replicating the whole database. The monitoring of the replication process typically provides good insights because these tools understand the data that is being replicated. It can happen that you encounter an application for which no replication tool exists. In such a situation, you will need to look for storage layer replication methods. Examples are self-replicated volumes or EBS backups to S3. Those replicate volume blocks, or Volsync, which replicates the file system. These tools lack any application-specific features, but on the other hand, because they are application agnostic, you can use the same tool to replicate data of various applications. When evaluating replication tools, I prefer to look at the application-specific tools first and what they have to offer. If these are not a good fit, I defer to the storage layer replication. In the last section of the video, I'm going to talk about applications in unknown state. I will show you how we dealt with them in our disaster recovery strategy. A region can fail in many different ways. A classic example is a disaster which was caused by an incorrect update in DNS or in the routing table. If a disaster happens in a region, it doesn't necessarily mean that the applications in that region are down. The applications can still be running, it's just that they may not be reachable from outside. If an application in such an unknown state accesses global resources, then we need to be careful. Let me show you on an example what the issue is. This diagram depicts an application that consists of two components, the publisher and the password changer. The publisher publishes messages to the third-party API. In order to publish a message, the publisher must authenticate itself to the third-party API using a password. The password is generated by the password changer. The password changer sets a new password in the third-party API, and after that, it shares the password with the publisher. Password changes like this happen periodically. Now, the issue with this application is that it cannot run in two regions at the same time. If we would run the application in the second region, then the password changers in both regions would be reaching out to the third-party API, and they would be resetting each other's passwords. So before we can fail this application over to the secondary region, we need to ensure that the password changer in the primary region stops updating the password. How can this be accomplished? There are two options. I call the first option infrastructure level fencing. The idea is that we can stop the password changer in the failed region by shutting down the infrastructure it is running on. Unfortunately, this requires access to the infrastructure, so it will work for private data centers, but not for a public cloud. If you are in the public cloud, then you can use the second option, which I call resource level fencing. This option prevents the global resource, the third-party API, to be modified by the password changer in the failed region, and this is accomplished by configuring the third-party API to revoke access for the password changer in the failed region. Let's review what we covered in this video. We discussed the DNS-based traffic routing, which allows us to fail over the application traffic between regions. I showed you our implementation, which leverages Route 53, the external DNS operator, and also the Argo CD. We talked about data replication between regions. There we discussed the crash-consistent backups, and we also compared the synchronous and asynchronous replication. Synchronous replication allows you to achieve a recovery point objective equals 0. However, this replication method might not perform well if the network connection between two replicas is slow or not reliable. On slow network connections, the asynchronous replication performs better. However, it cannot guarantee that there won't be any data lost during a disaster. Next, we discussed the differences between replicating on the application and on the storage layer. The application layer tools provide application-specific features that you may be interested in. Storage layer replication is, on the other hand, a generic approach that can be used to replicate data of various applications. In the last section of today's presentation, we discussed that due to a disaster, applications can get into an unknown state. In such a state, the application could still possibly access global resources. To ensure that the failed application is no longer able to access global resources, we can either ensure that the application is stopped, for example by shutting down the infrastructure on which the application was deployed, or we can modify the resource itself to prevent the failed application from accessing it. I hope you enjoyed today's video. Please feel free to leave your questions or comments down below. If you found this video helpful, please consider subscribing so that you're notified whenever I release a new video. Until next time.